Okay, so Maclaurin series is a way of writing any function that you've got as what we call a power series. So power series is, you've seen before from when we do binomial expansion, which is writing out brackets as powers of x, increasing powers of x. Turns out we can do this for any function, so we can do this for trig functions, we can do this for e's, for ln's, all sorts of different things, in a sort of similar-ish way to what you do with binomial expansion. Now I'm going to show you where this comes from, but ultimately this is a formula that is on your further maths formula sheet. So suppose we've got some function f of x and we want to write it as a power series. So we want to write it as powers of x with some coefficients a0, a1, a2, a3 and so on. Okay. The question is, how could we work out what a0, a1, a2 and whatever are? If we think about a0 first, what we could do is we could take f of x and we could substitute in 0. Because if I sub 0 into this, every term that's got x in will disappear and it will just leave behind a0. Okay? And so to work out a0, all I have to do is evaluate f of 0, whatever my original function is. Then the question is, how could we get a1? So I want to get a1 on its own without an x in it. Well, I could get that by differentiating f of x, because if I differentiate f of x, a0 disappears. If I differentiate a1x, that turns into a1. If I differentiate a2x squared, that becomes 2a2x. If I differentiate a3x cubed, that becomes 3a3x squared, and so on. If I evaluate this at 0, all terms with x disappear and they will just leave behind a1. So if I want to work out the coefficient a1, I differentiate my f of x and then sub in 0. And I can keep doing this to work out a2, a3, and so on. So if I differentiate this expression again, the a1 will disappear. 2a2x will differentiate to 2a2. 3a3x squared will differentiate to 6a3x, and so on. You would obviously get a squared term and a cubed term, and so on. If I substitute in 0 into this, then you'll just get left behind with 2a2, and so to work out a2, I'm going to differentiate f of x twice, and then divide it by 2. We do this once more, so differentiate 2a2, that disappears. Differentiate 6a3x, that gives me 6a3. You would then also get more terms, so you'd get another x term, and so on. In here, substitute 0 into this will just leave behind the 6a3, and so to work out a3, I do differentiate f of x 3 times and divide through by 6. Now notice the pattern here. What's going to happen is that each time you times it by another number for your coefficient. So what I mean by that is, for example, if you think about, let's put in a4 x to the 4 in here. If I differentiate this once, I'll get 4a4x cubed. If I differentiate this again, I'll get 4 times 3a4x squared. If I differentiate this again, I will get 4 times 3 times 2, a4x, and if I differentiate again, that will get rid of the x and just leave the a to the 4. Notice what we've got here is 4 factorial, okay? And this 6 here for a3, this is 3 factorial, and this 2 here for a2, this is 2 factorial. So a simpler way to write these a2 and a3 coefficients is f double dash of 0 over 2 factorial and f triple dash of 0 over 3 factorial. I say simpler, it's just so it's easier to see the pattern here. Okay. Therefore, this is the formula for the Maclaurin series of a function. Okay, so you basically differentiate it a bunch of times. You substitute in 0 to work out the coefficients, and then substitute into the formula. This formula is on your formula sheet, so you don't need to remember it, although it's not too difficult. If we think about e to the x for this first example here, so find the Maclaurin series for f(x) equals e to the x up to and including the x cubed term. All I'm going to do is differentiate my function a bunch of times and evaluate it at 0. So I start off with f of x equals e to the x, and then f of 0 is e to the 0, which is 1. Because it's e to the x, if I differentiate e to the x, I get the same thing. So every time I'm going to get e to the 0 and I'm going to get 1. And I need to go up to the third derivative. So f dash 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 of x equals e to the x. And then evaluate that at 0 gives me another 1. So all of these are 1. If I substitute this into the Maclaurin series formula, so f of x is equal to f of 0, which is 1, plus f dash to 0 x, which is x, plus f double dash to 0 over 2 factorial x squared, so that's half x squared, plus f triple dash to 0, which is 1 over 3 factorial, which is 6 x cubed, and so on. So this is the first 4 terms for the Maclaurin series for e to the x. We can use this to estimate these values. So unlike the binomial expansion, this does work for all values of x, not just small values. So e squared is the same as substituting 2 into this. Times 2 cubed. And if I evaluate this in my calculator, I get 19 over 3, 6.3 recurring. You can check this with the exact value of e squared in your calculator, which gives you 7.39, 7.4-ish. This is the right sort of ballpark. To get a better estimate for this, we could include more terms. For e to the 0.3, we can do the same thing. So substitute in 0.3 into your Maclaurin series. And you can get an estimate for this, which gives you 1.3495. And if you work out e to the 0.3, this is very, very close. So for smaller values of x, this is quite close, but it is valid for high values of x. Next one asks us to find the Maclaurin series for f of x is sine x. Make sure you're in radians because you're doing calculus with trig, so it should be in radians. So f of x is sine x, and if I work out f of 0, a lot of these terms are going to end up being 0. Differentiating sine x gives me cos x, and if I evaluate this at 0, I get 1. Differentiating cos x gives me minus sine x, and again, this gives me 0. So I need to keep going. Differentiating this again gives me minus cos x, which at 0 is minus 1. Currently, I'm up to the x cubed term, so I need to keep going up to x to the 5 term. So you can write this as f 4x equals, differentiating minus cos takes you to sine x. And we're back to subbing 0 in, and f5x, differentiating sine gives me cos x, which will give me another 1. So this is your x to the 5 term. Using your formula and sticking all of this in, say f of x is f of 0, which is 0. Then f dashed of 0, which is 1 times x. Then f double dashed of 0 times x squared over 2 factorial, which is 0. Then plus f triple dashed of 0 over 3 factorial times x cubed, plus another 0, and then plus 1 over 5 factorial x to the 5. Tidy this up, you can write this as x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5. There's no need to evaluate the factorials if you don't want to. It then asks us to use these first 3 terms to find an approximation for sine 20 degrees. So first off is to work out 20 degrees in radians by timesing by pi over 180. So you get pi over 9. You can then substitute this into your expansion. So you get pi over 9 minus 1 over 3 factorial pi over 9 cubed plus 1 over 5 factorial pi over 9 to the 5. Evaluate this and you'll get 0.342 36. So first off, it asks us for f of 0. So f of x is arctan plus x. So f of 0 is arctan 1, which is pi over 4. F dashed x, the result for differentiating arctan is on your formula sheet. So you can just quote that. So when you differentiate arctan x, you get 1 over 1 plus x squared. In this case, we've got a 1 plus x instead of that, so if I substitute this in, there's no number in front of the x to worry about for the chain rule. So I can just sub that straight in. And this is my f dashed x. I can evaluate this at 0, so if I sub in x is 0 into this, I'll get 1 over 2. Obviously it's a half. It also asks us to show that f double dashed of 0 is minus a half. So I need to differentiate this expression for f dashed x. I'm going to deal with it, simplify it a bit first, so I can differentiate it. So the first thing I'm going to do is expand out the bottom and write this as 1 over 2 plus 2x plus x squared. And then I'm going to write this as 2 plus 2x plus x squared to the minus 1, so I can use the chain rule on it. You could have used the quotient rule on the original function if you prefer. Differentiating this again, so differentiate the inside gives you 2 plus 2x. Differentiating the outside, so you times by the power and minus 1 from the power. Gives you that expression there. There's no need to simplify it because we're just subbing in 0. I don't actually need that expression. So if I sub in 0, my first bracket ends up being 2, then times minus 1, and then my second bracket also ends up being 2 to the minus 2, which will give me minus a half as required. Finally, it asks me for the Maclaurin series for fx up to and including x squared. So f of x is equal to f of 0, which we said is pi over 4, plus f dashed of 0 times x, plus f double dash of 0, which is minus a half, over 2 factorial times x squared. So I get pi over 4 plus a half x minus a quarter x squared.